Hello everyone and welcome back. We're hoping in this video will be relatively brief, just trying to finish out the section that we started last time. We want to talk about the compatibility properties of limits. Well, also colimits, but everything we're going to say is going to dualize nicely. So we'll just stick to one of these and just try to say everything that we need to say in order to finish out this section. And basically we'll prove two theorems in the next 15 or 20 minutes, which will give us compatibilities between limits and evaluations of a certain type. And then we'll talk about this theorem, right adjoints preserve limits. Okay, so to get started, let's make our suitable abstraction of an evaluation. So let's say we have two categories, J and C, where we're remembering that letters like I and J are small categories. These are basically our diagrams, or at least maybe the blank diagrams, and the functors between them are finished diagrams. And now let's say we have a map like so, row J, which will go from Cj, the functor category, to C, which works by taking gamma in the functor category, and this lives in here, and we'll take it and send it to J, yeah, that's right, sorry, gamma of J, I almost wrote J of gamma, I got confused. We're going to call these row J's evaluations. This is sort of maybe evaluating the diagram, if you like. Well, not the whole diagram, but at least this particular element. And with this definition, we have our first proposition. Let's say we have I to Cj, a functor. Then the forward limits of the alphas are the same thing as the forward limit of row J composed with alpha. And of course, in the same way, I didn't write this above, but I could have written beta, and then I guess I have to write I op Cj. But then in the same way, we obtain that the backwards limit here is the backwards limit here. And what is this really saying? Well, maybe another way of writing the limit of the alphas evaluated on J, if I take this guy, well, maybe another way of, how do I say this? Another way of expressing this equality would be to say that we can either evaluate on the limit, or we can evaluate each alpha and then take the limit, which I might write as like so. Sort of abusing this notation of alpha of J as sort of composing with this evaluation map. Okay. How do we prove this? Well, the proof is sort of straightforward. In fact, Kashiwara and Shapira don't even say anything about this at all, but I got confused, so I'll say a few words. We'll consider just the injective case. Yeah, I mean, this will be fine. Oh, wait, I said injective. This is the inductive. The inductive limit. And in order to prove this, we're just going to basically unravel the definitions here. And so what's going on? Well, on one hand, we have the inductive limit over here, which is, by definition, this is just the map, which takes x to, switches to the backwards limit, alpha x, and we're evaluating this on J, which is, of course, the same thing as using our Unita functors and evaluating this on J. And what we see is that this is exactly the same thing as sets which is all that matters because we're going to use the Unito lemma, as a limit of the alpha j, and the same proof works for the betas. The next thing is Kashiwara and Shapira upgrade this to bifunctors, which is a thing that they say that we might need, so we'll state it, but it's not tremendously difficult. Which is that if I have I and j both now two small categories, and then I assume, oh, I guess I needed to assume in the previous, no I didn't actually, but for this argument I need to assume that C has inductive limits of these shapes, namely, indexed by I and j. And suppose we have a bifunctor from I cross j to C. And now we get two induced, which sort of partial evaluations. The first is the partial evaluation in j, which sends I to Cj. And then we also have alpha I, which goes from j to Ci. It's basically just plugging in the respective arguments. Then the limit of alpha exists, and we have some equations. We can do the limits component-wise, first j and then in I, and this computes the whole thing. But we can also do this first in I, and then take the limit that way, and that's fine too. And the proof of this is basically just to do the same argument twice. You have to keep track of the order in which you want to consider the arguments, but this is basically a trivial upgrade of what we just did. Okay, to finish this out, I want to give the argument. I probably should have just done this at the end of the previous video, but what are you going to do? Let's talk about this business of adjoints and limits. So suppose we have f c to d, some functor, and I is a category. We're going to make the following assumption, which will be that C admits, sorry, I almost said, I'm getting ahead of myself. I want C to admit inductive limits. I almost started talking about the adjoints, but we're not there yet. C admits inductive limits indexed by I. And in this case, we say F commutes with such limits. Really, F commutes with the inductive limits indexed by I, but I'm not going to write that again. If for any alpha I to C, then the limit of F compose alpha exists in D and is represented by F of the limit object. So this is, of course, we're just literally commuting F with its limit. And I'm not going to rewrite the whole thing. I'm just going to write similarly for beta projective limit. And then I'll write the backwards limit of beta composed with, no, other way. F composed with beta. F of the limit. Okay. So with this definition, we're ready to give this argument. Nice and clean proposition. So as above, F will be some functor. and we'll assume F admits a left adjoint, which we'll call G, which will of course go in the reverse direction. And we assume that C admits projective limits indexed by I. In practice, I mean, when you're actually doing these calculations, the categories you're interested in are always complete or co-complete. So it's no big deal. And then I claim F commutes with projective limits indexed by I. Whoa, that got really squiggly. Sorry about that. Okay, well, and the proof is very straightforward. This is like the cleanest calculation we've done so far. We start in D, and we look at the f of the limit, and now our adjunction tells us that we can write this as a hom in C of G of Y. That's what adjunctions let us do. And we have the backwards limit over here. But now we know that limits pass through homs, and when they're in the second argument, the direction stays the same. So this gets us G of Y of beta. And now we just use the adjunction again. To go back over here. And this complete, oh, I wrote hom C again, but I should have written hom D, because when you use the adjunction, you got to switch them. And this finishes our argument once we realize that we can then, again, by definition, pass the limit back inside. And of course, in general, use the unita lemma. And this finishes our proof. So this is sort of the slickest and nicest computation that I think that we've seen yet. It's certainly typical in my experience of what it means to do a calculation in category theory. Typically, when one wants to show that something commutes with something else, you have some universal property or a definition of sorts that tells you what sorts of manipulations are permissible, and then the game is to just make some sequence of manipulations that allows you to do the thing you want to do. And in this case, what we do is, well, we want to switch the f and the limit. They're sort of in the way of each other, so I push one out of the way, and then I use the properties that I have at my disposal. I can move the limit out, and now once the limit is outside, I can use my adjunction freely. I put the f back, and then the limit goes back, and they've indeed been switched. As a closing remark, this theorem has a name, or at least a nice shorthand, which is often called right adjoints preserve limits, RAPL. This is not exactly the way we've stated it. In the hypothesis, we said that F admits a left adjoint because that's what Kashiwara and Shapira say. But of course, if F admits a left adjoint, then F is a right adjoint to something else. And in this case, we remember that the projective limits, well, these are the backwards. These are the backwards limits. These are also the ones that we call limits because category theory terminology is annoying. And so this is right adjoints preserve limits. And if you have a hard time remembering that, then just remember here that I have this PL, and that's both stands for preserve limits, but it can also stand for projective limit. And therefore, you know that you're looking for the backwards ones must be the ordinary limits, TM, and it's the co-limits that point forward. And I'm not even going to touch on this business of direct and inverse limit because it's the same thing, but the terminology is backwards. So we'll just not worry about this. And as a closing remark, as always, you can dualize if you want. You can obtain a theorem which you might call left adjoints preserve co-limits if you wanted to. But you're not under any obligation to do that here in this video. You can do that yourself if you want to. Okay, next time we pick up where we left off with examples. We want to do as many examples as humanly possible. I wanted to do the examples first, but everything in Kashiwara and Shapiro is sort of at a very abstract level of generality. And when I was trying to write notes on like how best to explain the examples, I found myself wanting to either refer to these facts or needing to unpack what they were saying, and I just came to the conclusion that maybe they were right to put the general theory first for their own exposition. Of course, they're smart guys. Like I'm sure that they thought this through. But I've never found anything in category theory motivating without a collection of examples at hand. And so next time I promise to actually deliver on those, and hopefully that will clear up any mysteries that you may experience in your brain about why one is making all these abstract definitions. Okay, then in that case, I'll see you guys next time.